Hi everyone, very happy to be here. My name is Peter. I'm actually really excited to be here at all because I was supposed to be here on Thursday evening, but I arrived last night at 8. I arrived in Denver on Thursday, and then my bus got canceled due to a snowstorm. Because you can't just come to Colorado and not have a snowstorm and fuck up your trip. It's what you pay for in the flight. And I'm also still waiting for the bear mauling experience. But anyway, so I slept in the train station, which if you were planning to sleep in the train station, I don't recommend it. But yeah, so then I took the train last morning, sorry. And then all the things happened, like rocks on the railroad, and there was a fist fight in the train, so someone had to call an ambulance, and I guess one of them lost, one of them won. But yeah, happy to be here. Okay, so this talk is about clang and LLVM. It's a topic I find very exciting because I think it's important for everyone. And to some extent, I liken it to taking some of the power of the omnipotent compilers and giving it to the people, to the mortal developers. Because as you'll see, clang is actually really just a very, very awesome library that you can use for reflection on steroids. And reflection in the sense that it's not reflection of your current program, but reflection of some other program. And you have the entire power of the compiler, which has a lot of power because it needs to actually compile your program. All right, so very quickly about me. And I wanted to keep the slide short, so I compressed my entire CV into one word. So I'm a second-year CS student in Munich. And right now I'm at Facebook doing an internship. I just started on Monday. Before that, I was at an AI startup. Before that, at Bloomberg. Before that, at Google. And after that, I'll be at MIT doing a machine learning research internship. So my interests are generally schizophrenic between C++ and machine learning. All right, so jumping right in. So this talk is about Clang, of course, but I nevertheless want to give a bit of a sweeping overview of LLVM because I think it's a very interesting project and because I think it's also good to know where Clang tooling fits into the entire compiler toolchain, so we know where we're actually entering the pipeline. So LLVM is a toolchain for compiling, and once upon a time it stood for low-level virtual machine. It doesn't anymore. Now it's just an umbrella term for a number of different tools and projects built on top of the LLVM stack. So you have the LLVM debugger, you have the optimizer, which is really the core of LLVM, the LLVM linker, and even LLJVM, which compiles C to Java bytecode. I know that those people exist. And then there's a bunch of programming languages, of course, built on top of LLVM. So you have Clang, which doesn't have its own logo, unfortunately. You have Swift, which was also designed by the designer of LLVM, Chris Lattner. He worked at Apple for 10, 15 years. Now he works at Tesla as the VP of Autopilot software, working on electric compilers. And the funny thing is actually that Tesla uses GCC, so too bad for him. And then there's also Rust and even TensorFlow. So the Google's machine learning library uses LLVM to compile computational graphs for machine learning to fuse operations and just-in-time compile things, even in a distributed, on very many nodes. So LLVM is really awesome. There's, of course, loads more projects and languages built on top of LLVM. Then I'd like to talk a little bit about compilers. So of course, this is not supposed to be an intro to compilers, but I think it's nevertheless interesting to understand what Clang actually is and what LLVM is and where we're actually working. So in general, nowadays, compilers have a three-phase design consisting of a front end, of an optimizer, and of a back end. So the front end is responsible for parsing, so tokenizing your code, lexical and semantic analysis, building an AC. The optimizer will then take an intermediate representation of your code and perform lots of optimizations on it, hopefully, to make it faster and leaner. And then the backend is responsible for taking that intermediate representation and turning it into architecture or target-specific machine code or object code. Then the basic benefit, or most important benefit, of this three-phase design is that if you have these three separate parts, you can have many different front ends all using the same optimizer and backend. And you can have many different backends all using the same optimizer, so intermediate representation. So this is actually really essential and crucial because if you didn't have this, just in this case, you would have to have 9 different compilers for just 3 languages and 3 backends. Whereas in this case, you can add any backend for some new microcontroller or some new system you might be developing, which actually turns out most people using LLVM do. So you have lots of companies who develop ASICs or special chips, and they use LLVM to compile stuff to these specific targets. And of course, you could have many different front ends for your own language, for new languages, and so on. Now, a little bit more about LLVM in this case. So in the case of Clang and LLVM, the front end is split up into the lexer and parser. At this point, we would be dealing with .c or .cpp or .m, so Objective-C files as well. And we would be lexing it, turning it into an AST. Then the optimizer is really a set of passes. And at this point, we would be dealing with .ll, which is the LLVM intermediate representation of files, and also .bc, which is a bitcode representation. And this is actually really the core of LLVM and the core benefit. So GCC actually only got this very late, only in the past few years, this intermediate representation, and it's really very important for all of LLVM. And so in case of, for example, the LLVM optimizer, you would have const prop pass, which would try to plop constants throughout your code. Then LICM, which is loop independent code motion, which tries to take declarations out of loop, so you don't do it in every single pass of the loop, like if you're declaring some constant. Then, of course, inlining and loop unrolling. So these would be passing through. I think there's like 60 to 100 passes running every single time you run clang. And that, of course, is very important. And then the backend does machine-dependent optimization and will emit .o or .s files. So machine-dependent optimization is basically the idea, or the goal here is to take the intermediate representation and map it as efficiently as possible to the target architecture. So for example, in the case of like x86 or CISC architecture, where you have instructions for everything, like copying a register to another register and AES encrypting your hard disk and tweeting about it all in one instruction. The goal here is really to take lots of instructions and mapping it to a single one on the target architecture. And then also doing things like register allocation, which is actually a very interesting and difficult problem, where in a program you have lots of different values alive at different times, and you need to map them to registers. And in the case of x86, which has only very few registers, this is very hard. And then in the end, you have the code generation, where you emit the actual assembly code or object files, and then pass that onto the linker. And we'll be dealing mostly with the front end, of course, because that's what Clang is, Clang front end. Now, looking a bit more closely at Clang, let's look at what the lexing and parsing steps would do in the case of Clang, because this is also where we'll be operating. This is our playground for today. So the lexer would first of all take this C++ code you just saw and tokenize it. So split it up, and so take these raw characters and split it up into many different annotated tokens. So in this case here, we would have like keyword for template. We would have the less token, another keyword, identifiers, and so on. And so this is the output of the lexer. And at this point, I'd like to just jump into some code. And also one goal for the talk today is just to give you like a very sweeping overview of the Clang and LLVM code base. So can people see this? All right, so this is Clang. It's actually a very, very nice and beautiful code base. So given the fact that it's almost 15 years old, it's probably one of the best maintained projects out there in the wild. Seriously, like probably top 3 or even the best one. It has very clean code. It's very well optimized. So how many people saw Chandler's talk on like LLVM data structures a few years ago? Okay, so you'll probably, and I'll also talk a bit about that later. But so the only quirk is that variables are uppercase, or capitalized, sorry, which is a bit of a problem if your class has the same name as your variable. But other than that, it's actually very, very nice code. So you can imagine for a lexer, this would end up being just a very large switch case statement, and it really is, like this is a switch case. And so for example, if we were to read the R token, then if this is a C++11 compiler, R could mean raw string literal. So we would try to lex some more, like try to see if there's a this quote symbol afterwards. And otherwise, if it's not C++11, it's just a normal identifier character. And then we have that for all other kinds of characters, of course. OK, so after the lexing step, we have a stream of tokens. And then it's the job of the parser to take the stream of tokens and build an abstract syntax tree out of it. So in this case, we would have this function declaration from the code you saw before. And we would have a CXX method decal in Clang terminology. And at this point, also remind yourself that Clang is not just a C++ compiler, but also a C and especially Objective-C compiler, which is probably the furthest from C++. So everything that's C++ related has a CXX in front of it. And you would have a method decal. Then you would have, in this case, a return type, a parm_var decal, and an isconst, where the isconst is because this is a member function. Then the parm_var decal would have a default argument, would have a qual type, an identifier. And the qual type would have a type inside, because a qual type just adds like const or volatile qualifications to a type. And then above that, you have a CXX record decal. And the record is a struct, class, or union. And then above that, the top level will always be the translation unit decal. And then you have lots more beneath that. And this is actually really nice, because the Clang has a very rich AST, which you can access, which you can work with, and which you will like to work with later on. Now, once we have this AST, the next step in the LLVM pipeline, and this is actually also where we'll stop, is taking this AST and transforming it into LLVM intermediate representation. So this would basically have something walk the AST, and for each node in the AST emit some LLVM. And this actually also, so this is if you were to write your own front end, at this point you could stop, because that's all you need to do. As soon as you have some way of transforming your quirky brainfuck language into LLVM intermediate representation, you can use the entire power of LLVM. You can write that to any backend. You can use all the optimizations. And that's actually very powerful. So at this case, in this point, for example, if you wanted to, is this that? Let's go up a bit. Let me show you what this intermediate representation would look like. So I have this test file here, for example. It just has a function. And if I wanted to emit LLVM, I have this command here, -s and minus emit LLVM. And this will emit this test.ll file, and we can see what this actually did. So in this case, this is very unoptimized. If I actually turn it to like 03, there would be literally nothing left because nothing is actually using this. And you can also see that there was this class, which no one uses, so it's also gone. But what you can see here is that the LLVM intermediate representation is actually a RISC instruction set on its own. So it has some nice properties, like it's strongly typed. It has some higher level constructs like defining functions or calling functions or returning from functions, because that basically abstracts away the calling conventions that you would have on a normal architecture. And then you also have infinite registers. So this is also the reason why it's a virtual machine and not a real machine. You have infinite registers because that makes analysis a lot easier. So whenever you would like increment a variable, like we did up here, like this plus equals 1, that would actually store, for example, from 2 into a new variable %3, because that makes it easier to understand what's going on. It's basically like if you were to split up your program into lots of different declarations and each one were const, it's of course easier to understand what each line does, even though it's maybe a bit more verbose. Okay, then let's talk a bit more about the clang AST. So this is what we'll be playing with today. So we have this statement here, and there's 4 major classes when we're using clang. The first one is statements. So a statement is a lot of things. So in this case, for example, we have an if statement, which has a condition that is checking and some code in between. And I'd like to also show maybe here some doxygen. So clang doesn't have that much like inline documentation, but the doxygen is very nice. So you can see there's a few statements, a few different kinds of statements. And a statement would have, for example, in this case, we have an if statement. And an if statement has something like a condition expression. It has a then statement, which is anything inside after the if. It also has a corresponding else statement, and we can get locations. And there's also this interesting get in it. So does anyone have an idea why if clause would need an initializer?
Because you can declare variables as a condition of the if in C++17.
Yeah, exactly. So like if we just pop up like this if statement here, and we can see that, for example, so if you've never seen this, we could have some if statement here in C++17, where we declare a variable and then have a like semicolon and then actually check some condition after the if clause. So this is actually a very nice new feature that I encourage you to use with Clang, of course. And yeah, so that's what you would be dealing with. And there's of course lots more beneath this AST. Then after statements, we have declarations. So declarations could be anything from a class declaration, variable declaration, function declaration. And also if we go to the doxygen for decal, it's even larger. So there's really loads of different declarations. Anything from like declaring an enum, I think is somewhere here. Then name declarations, which would be like classes. And then even here, there's value declarations. And then if we're actually interested in like looking at the, we have this open. In actual like fields or variables, there's even more behind this. So LLVM does use inheritance and polymorphism a bit, and quite a lot. So you'll see this very much. And so for example, here, way down the inheritance chain, you would have a field declaration inside a class, or you would have a variable or a function. And that's what you would be working with. OK, then after declarations, you have expressions. And this is actually a bit of a quirk inside of the Clang architecture, that an expression actually derives from statements. So intuitively, this doesn't actually make sense because an expression is not a statement. You would think that a statement has an expression and is terminated by a semicolon. but that's the case. So for example, here the condition would be an expression, and also the string literal would be an expression. But the fact that expression inherits from statement also means that you can't actually represent the semicolon, like the no-op, in clang. Like there's no way to actually represent it, which is a bit funny. Yeah.
Just not get represented in the AST at all?
No, because like you would basically, like if you had it with a, sorry, the question was, does it not get represented in the AST at all? I believe it doesn't, because like if you had the has a relationship, you could just say like a no-op would be a statement without an expression. But in this case, I'm not sure what it does, but I know that it can't be represented very well inside the AST. And the last thing then is types. So types are obviously important, especially in C++. In this case here, we have a const char pointer type declaration. And then beyond types, you have qual types. So a qual type contains a type inside and adds some qualifications. And we can actually look at this. It's quite cool. So this is actually more related to Chandler's talk that I mentioned before. So if we go to qual type, then this here is really this is the entire LLVM philosophy that Chandler talked about in his talk in one class. So a qual type basically has a pointer to a type. And this is also, if you remember, Chandler said that if you have big objects like types that you use everywhere in your program, then sometimes it's just a good idea to actually allocate them once and just have pointers to them. And that's what LLVM and Clang do. And then we add some more quirkiness. So first of all, if you just ignore this in between here, what this pointer int pair does is it uses the lower 4 bits of every pointer. If you don't know, like malloc usually allocates in 16-byte boundaries, so the lower 4 bits are up for grabs, and LLVM does grab them. So here we have a pointer int pair. The pointer is to the type, and then we can use the lower 4 bits for const or non-const, volatile or non-volatile, and additional qualifications. So that already saves us some space. And then the next step is that if we needed more qualifiers, then we have a pointer union, which would actually, instead of pointing to the type, would instead point to an external structure which contains the type and more qualifiers. So like in 99.9% of cases, you would just have this one pointer using the lower bits. But if you need more, then you can just then the same pointer will point somewhere else. And so that's actually really maximally space efficient, which is very nice. OK, now we get to clanging all the things, talking a bit more about Clang tooling. libclang, libtooling, and then we can spend the rest of our time looking at some code. So the first thing we have in Clang tooling is libclang. So there's these two basic libraries. There's libclang, there's libtooling. Libclang is the C interface. And the one thing that's special about libclang, apart from it being in C, is that it's the stable API. So one of Chris Latner's, so founder of LLVM, and general LLVM community's philosophy is just to break all the eggs. So whenever something needs to be changed in the intermediate representation, just break it. Break everything that depends on it, because we need to move forward. And that's good for the project, but it's bad for everyone depending on it. So for this case, if you're developing an editor, for example, you don't want to update your code after every release. So libclang is the stable C interface. So libclang basically never changes. It probably was designed once. And it has a clean interface that won't change very much in the next few years. So if you're writing an editor, you can use libclang and rely on it not changing that much. So here's some libclang code, and we'll walk through some real code after. But just to give you an idea, libclang has this basic concept of cursors. A cursor is just like a pointer to a node. And then we have visitation. So one thing I forgot to mention about these different expr and dictyl and type nodes is that there is no common AST node in Clang. So there's no base class for all kinds of nodes. And the main implication of this is that whenever we want to walk the AST, we're never going to be able to just have a function like this here in C, where we have a cursor, where we can take any kind of node. So anytime we want to walk the AST in the C++ API, we're going to be using visitation. So we'll have a class that we override, and then we override the visit decl, visit type, visit statement functions. And that's actually a very important part of Clang as well. So in this case, we would have a cursor, which is just a pointer to a node. We would be getting its location, checking if it's the main file or not from system header. And then we would be getting its spelling, print it, and then in proper RAII fashion, disposing it. And then this line down here just tells it to recurse. And we would be giving this to some low-level C API, and it would do most of the magic for us. Another thing that's cool about libclang is that it has built-in code completion. And this is actually very important because literally if you want to like get code completion for your code, there's one function called code complete at, which you pass a buffer and pass a location, and it will tell you all the possible completions at that point. So what Clang does here is that when you tell it to code complete at, it will insert a special marker in the AST, and then when it parses and reaches that specific point, it will use all the context it has, all the everything it knows about the AST at that point to give you full information about how you could complete the code at that point. So there's those functions and a few more like very nice high-level functions. And also what's nice about libclang, or maybe nice, is that it has a Python API. So this is the exact same code in Python. You know, not saying anything, not saying that one is better. But this one is quite readable. It's also like it's even more high level. And this is probably useful because lots of editors, like I think Sublime uses Python, and Atom uses JavaScript. So having like scripting languages on top of the C APIs is actually very useful. Then we have libtooling. Sorry, yeah.
So is there a C++ API on top of it also? Just something that handles all of the RAI, iterators, ranges, or is that a role that you're up to sell?
So the question was if there's a C++ API. There is, but not for libclang. So libclang is like the C API, and then there's the very powerful libtooling library, which you use for everything else. Yeah, and that's what you're looking at. So libtooling is the C++ library, and one thing to note about libclang is that because it's so stable, it's very high level as well. So even though it's nice, and like if you can achieve something with libclang, I would definitely try to achieve it with libclang because it's less code, it's usually easier. But very often you'll just get stuck because there's something you want to do and libclang doesn't expose it, and that's where you usually want to use libtooling. And I actually also prefer libtooling because it's C++ and it's a lot more powerful. So with libtooling, and we're going to look at some code in a bit, but there's three basic kinds of doing tooling. The first thing is clang tidy. So how many people here know clang tidy? Yeah, so the first way of adding or writing a clang tool is to integrate directly with clang tidy. So here you would basically be adding a new plugin to clang tidy and be adding it to one of its checks. The nice thing about this is that it abstracts away a lot of the boilerplate, but you're also bound to clang tidy, and you can't just have like an external tool. Then we have Clang plugins. So Clang plugins are essentially the same as the last one, which is Clang tools, except for the fact that Clang plugins are dynamic libraries that you build and that you link into Clang when you run it. And it's also a bit more complex to actually pass it to Clang. But the nice thing about like Clang plugins is that you could just, for example, put it into your like build tool and it would run checks when you compile and make sure that you're not like violating any like linter errors or anything. But the last one is writing a Clang tool, and this is actually what I prefer doing, which is really just writing a standalone executable using Clang as a library. And this is really cool because you get a standalone thing that you can drop into places, and you have all the power about the, you actually have a main function. So in the case of Clang plugin, you don't have a main function, so you can't do first of all, you can't keep state in some cases, but you also can't do emit some JSON at the end or something because you don't actually know when it ends. So Clang tooling gives you all the power. Clang tool gives you all the power. All right, so this picture should tell you that we're going to have some fun now. And so I brought a lot of tools. And actually, I brought too many tools. So because I had so much time on the train here, I decided to make this slightly interactive. So I made this. I hope this loads. I made this HTML17 website where you can actually vote. You're going to be voting now what tools you want to see. So please bring out your phones and bring out your Wi-Fi. I'm just going to walk briefly describe each one, and then you can. So this HTML17 website has a REST API, of course, and then you can vote for it. So let me just walk through each one. So AST dump is the first one. It uses libclang, so the C library, and it just dumps the AST. So what it does actually is, if we have some code here, yes. So if there's this ast dump thing you can do with Clang, which is actually very cool. And it basically just dumps the AST with all the information about the types and variable names and everything. And ast dump would be rewriting that in libclang, which is actually very educational because you'll see how we can access all of this information through libclang. So that's the first one. The next one is CPP grep. So sometimes you might have this problem, like if you have an editor and you want to look for the word, I don't know, like class, it'll be everywhere, right? Like you have a class keyword, you have class comment, and if you have some variable named, I don't know, Phil, you might have a class named Phil and everything named Phil. So what CPP grep does is it's also using libclang. It's like grep, but you can actually like filter by functions, like C++ functions or C++ records, and so on. So it's quite cool. Then dict check. So a while ago, I was working on a programming university, and my fellow co-developers weren't so fond of readable variable names. So because I was a team lead, I decided to write a tool that would run through their code and make sure that every variable is a word in the dictionary. And so dict check does that. It's actually very short and fun. Include sorters, you can imagine what it does. This is so dict check and include sorter. Include sorter just sorts includes are both lib tooling. Then minus tool is more of a educational one to show you how diagnostics work in Clang. So if you're interested in how diagnostics and fixits work, that one's pretty cool. Then use override checks that you use override on your methods. So this is more into the region of making sure that you as a developer write safe code. Virtual destructor makes sure you use virtual if you ever derive from a class, even if you don't declare the constructor at all. Using lib tooling and Clang variables is if you're interested in how to do some extreme kind of matching. So you want to find, so Clang actually stands for const lambda that takes an auto variable, is declared no except, and has a goto inside. So if you're interested in finding exactly some particular node, this tool is quite interesting. CPP grep pi is the same thing as CPP grep, but in Python, and half the amount of code. Enable if checks that you use enable if underscore t instead of type name enable if. So it's more like modernization, which is cool. Maccabi, this one is quite nice. Have you ever heard of Maccabi computational cyclomatic complexity? So this is basically, it's a measure of how complex your code is, how many paths there are through your code. It's actually very interesting to know because if you have lots of if clauses in your code, you should probably refactor things or rethink your design. So this tool actually does that. It sounds very complex, but it's just 3 lines. But it also shows you how to access the control flow graph in Clang. Then we have pointer finder, which finds pointers. So previously I was at Bloomberg, and in Bloomberg we have this style rule that every pointer has to be prefixed with p underscore. And so this tool finds all pointers, make sure they're prefixed. And then using versus type defs finds all type defs and recommends to use using statements instead. Okay, so the way we're going to do this is, so this I unfortunately did not have the time to register a domain name. But so if you can people see this? Yeah, let me just. So this is the URL, and I'm going to put it. Let me just join these two here. Why is this Twitter? Okay, so if you follow that URL and then do a vote and then /12, these are the bold numbers here. And if you type that, let me just show you. If you type that in here, then it may explode. No, it does not explode. So it basically thanks for voting. And then if I reload this page, I just voted, right? So just do this. Can anyone see this IP address? And just a comma-separated list of the numbers in bold, and that will make you vote.
So we can vote early and often?
Yeah, don't cheat. Don't vote, and don't DDoS my server.
On my phone.
Yeah. As I'm just.
How fast can you type?
Yeah, so I'll just do that for 2 minutes or something. In the meantime. Oh, well, it's loading very slowly.
I think it didn't back it.
Okay, I mean, worst case, I'm just going to pick some dictatorially, but I thought this would be fun. Oh, is it still running? Yeah, okay. It is still live, so if we, indeed, okay. So let's just wait 3 more minutes. In the meantime, if you have any questions, I'm happy to answer. Okay. But I think people are, does anyone need more time?
Wait. What's the number?
You want the bold numbers. So I made it so that they don't actually change, so you don't have to look where everything moved, even though the rank actually changes. Yeah. So I think if this manages to load, then we'll just pick that. Ooh. I should have sharded this probably a few more times. Okay, so let's just stop it here. Thanks for your vote. I hope democracy is a nice thing, as long as it doesn't get Trump as president. Sorry?
Do you get any reply?
Yeah, it says like thanks for voting, and the tools that you picked. All right. Okay. So we have CPP grep, Maccabi, include sorter, and so on. All right. So we'll just start with CPP grep. Yes, live, very live. So live. Okay. CPP grep. Okay. So this was libclang, as I said. Let's just start at the very bottom. It's reasonably lots of code. And I'll just walk through it. So libclang, first of all, LLVM is a very nice command line library. It's actually like the nicest one I've seen so far. The only detriment is that it uses global variables for everything. So if you're linking with some other library that also declares flags, you'll have those flags as well. But nevertheless, so the first thing you always do with libclang is create an index. And an index is like a structure that will manage all your translation units for you. And then you can also use precompiled headers, which makes your code a lot faster, or your parsing a lot faster, of course, especially for like standard headers. And then, what this tool actually, how you use it, let me just go here, CPP grep. So I can say at this point, I've spent a significant amount of my life trying to compile LLVM and clang. Like if you made a pie chart of my life, the slice would be visible. So I've now moved to just using Docker with like the LLVM library installed via apt. So let's just show you what this does. So CPP grep, the way you will use it is like some pattern, for example, and then the file. And then it'll just show you like the lines and everything. And then you have you can filter by functions, you can filter by members, parameters, records, so classes or structs, variables, and you can make it case insensitive. So that's what we're building. Nope. All right, so then for every file, we're just going to read the lines. We're going to need those lines later on because we want to write out the entire line where we found a match. But that's just a detail. Then we have this parse function. And what parse does is it calls clang parse translation unit. So this is a very important function because it actually gives you back the entire AST. So this does all the parsing. You pass it this index. You pass it a file name. And you can also pass it some buffers. So this is important if you actually have an editor and you have some unstored buffers. You can actually just pass those buffers to Clang. It will also parse those for you. And then at the end, we have this CX translation unit, which is a cursor as well. And then once we have this translation unit, we can get a cursor, and then call Clang visit children. And this is this important function, which I showed you before, which does the actual visitation. So this will walk the AST. And what you do with it is you pass it a cursor, like the top level one, usually the translation unit. You pass it a function, which is further up there, and you pass it some data. So data is just like void star, type erased, C++, or C polymorphism style. And then the data here includes a filter and the lines. And the filter just, in this case, it has some predicates, right? So you can imagine we have some code. We want to pass it through some filters and see if it still matches those. So we would have a pattern, which is like a regular expression. And then some predicates, which are just functions that take a cursor and return true or false. And where we actually declare them is inside this function here. So this make filter, which we call at the very beginning, it will check all the options in the global scope, of course, and then add some filters. So for example, if we only want functions, then we would get the cursor, and we would get the kind of the cursor. So every cursor has a kind, and a kind is basically the C abstraction for decal or statement or expression. And then we would check, in this case, if we want it to be a member, then member function should be a method. So we would check if the kind is CXX method, right? Otherwise, we would check if it's either a function declaration or a method. Then for a variable, we would check if it's a member variable. Member variable means field, so we would check if it's a field. Otherwise, check if it's a variable or a field. Parameter checks for parm decals. So all these nodes that you saw before, they are also in Clang. This one here like if you only pass member, it will look for all functions and fields automatically, so field or methods. And for records, it will look for all structs or classes. So these are our filters, and what we need to do now is walk through the AST, look at every node, and just ask our filter, does it match? And this is what the grep function does. So this is what we pass to this clang visit children function. And we get a cursor. This here is the parent, which we don't need in this case. Nope. But we would have that, and this void star client data. So the first thing we do down here then, for example, would be casting that back to our data pointer so we could access our stuff. Before that, we just check if it's in the system header, because if you write any tool and you forget this, and you include a standard header, you will get loads and loads of different matches for everything, which is very bad, because it's a huge AST. And then so we would get our data. Data includes the filter. We just ask the filter if the cursor matches. So this would also check one filter, which is the pattern filter. So this uses C++11 regexes. We get the pattern is from the command line, and we would make a regular expression and make it possibly case insensitive, and then just add that as another filter, right? So we and then to actually check it, we would call get cursor spelling. So spelling again is just the name of whatever is our node. So it's the name of the function, name of the class, and then we would just do a regex search and see if it matches, and that will be our one of our filters. So if we go back to grep, we will check if it matches, and if it does match, all we need to do is display it. And so here we need those lines that we also have in our data. But what we first need to do is we have a cursor. We want to find out where in the file is this cursor. So we call this funky function called clang get spelling location, returns to us line number, column number, and file. And then after some assertions, if we have more than one file, we also want to display the file. So if I actually pass the same file twice, we would get the file name there as well. We would print the file name, and then some escape codes. This probably won't work in Windows, but some escape codes, but then the line number, the column number. And what this here does is, so this one here, it gets a line from all the lines in our file, and then it runs through each character. And if we get to the actual node that we matched, it just throws in those escape codes so that it turns up red and bold. But essentially, that's all there is to it. And then at the end of grep, where's grep? We return cx child visit recurse. So there's 3 different things you could return here. This one here tells clang to continue recursing through the AST. Then there's cx child visit continue, which would tell it to go to a sibling. So for example, if you are at a function and you figure out you're absolutely not interested in anything below this function, like the statements inside, you can just continue to the next sibling, which is the next function. Or you could just cx child visit break, so just stop at this point and bottom up again. Yes?
Question, you showed that function where you access the current location of the cursor.
Yeah.
Why doesn't that just return a struct with the 3 elements and have these 3?
Because it's C. Because it's C. Because it's C.
Oh, the API is C.
Okay. Yeah.
In C you could return a struct.
Yeah, but I think in C it's customary to have your functions have 20 parameters and return
I
a.
was teaching C in the 1980s, and everything more than 3 parameters is something you should consider.
Yeah, absolutely. I mean, also this function here is way too long, of course. But also, actually, one thing that's I found this code guideline from LLVM quite interesting. If you have lots of parameters, you just put inline that Python keyword style arguments. It's actually quite useful. But so anyway, that's actually, I believe, all there is to this one here. So we would just print the match, and then if we try this out, so here we are. We have I can compile this again. It'll just take very long. The reason why it takes long is that this was supposed to be more impressive. This is why it takes very long to link. So this is all the LLVM libraries you're linking with. Here they're just all in one library, but it's still a huge amount of libraries you're linking with. So it takes like a minute. We don't have that minute. So if we now try to use it, so we have test.cpp. And so the point of this tool, right, is that if we just do grep on this, and we want to look for all x's, we're going to get all the x's. If I had comments that described what x is, I would get the comments back. So what we do instead is we call cpp grep, and we say that we only want functions that are called x. And so what does it do? So let's just like walk through it very briefly. It would like go have a function option, so it would add the function filter and the regular expression for x. And then here appear in the grep function, we would just have like two filters, which are called inside this filter class. Like, so it first checks the pattern. If no filters are passed, it just accepts anything that matches the pattern. Otherwise, it checks if any of the filters pass, right? In this case, the function filter passes. And if we also wanted to include like variables in here, we also get the variables. So this is actually quite cool. I don't know, I'm sure like some Visual Studio editors or something do this as well, but for Vim people or other Atom people, this is not there. So this is the first tool. Yes?
When you were parsing the AST, what was the function you gave it? The one that actually translate the translation unit function. Yeah.
Yeah.
Do you have an option to pass in include files there at that point, and include directories for having it search? Yeah,
you have. So I didn't actually do this here, but like these command line args, so you would want to fill this out in practice. Mm-hmm. So you would like pass -e and minus I, sorry, and then like the directories you want to.
But it'll implicitly find the system headers. But if there's any additional headers in this example,
it actually won't find the system headers, which is a problem because the question was. Can you pass includes? It won't actually find the system headers because, so the reason why Clang finds system headers when it compiles is because you're using the Clang driver, which like knows everything about your system. But here you're using like Clang directly, so Clang knows nothing about like C++ standard headers are just some headers. So you would also need to pass those, but yeah.
But it would know when it is parsing a standard header versus another header versus the translation unit itself. That's an option that you can get during the callback.
Yeah, so the question was, would it know about the system headers? It does have like this stuff here, so you can check. So like this is like Clang does try to tell you whether or not it's a system header, and you can also even check like whether or not a node is from the C++ standard library. Like it knows about that as well. So yeah, you would want to check this. There's also like is in main file, which checks if it's in the main file instead of like a system header. But so yeah, that's possible.
You can also check a particular node and see what the enclosing namespace is. And if it's in STD.
Yeah, exactly. That's also possible. Okay, so I think the next one was Maccabi. So this here is libtooling. So it's actually good that we switched to this one as well. So this is the C++ API, which of course is a lot nicer. And the cool thing about like libtooling is that you're not actually there's lots of levels of abstraction that Clang has added on top. So libtooling is developed primarily by Google Munich. So Chandler's team and Chandler's team in Munich are doing huge efforts to make tooling very easy. So there's already like Clang tooling libraries here. And yeah, so let's just try this out. So we would have, so a Clang tool, first of all, is made up of three distinct things. You have an action, you have a consumer, and then you have some kind of callback. So what an action does, first of all, let's just like walk through it. An action allows you to access the AST at different steps during the compilation. So for example, in this case here, we have an action, and we could override begin source file action, which would be called before every file. So at this point, we could like look at the compiler instance and like get options of the compiler. So in this case, for example, just to show off what it does, you could ask the compiler for the language options, which are like, is it C++11? It even knows, are we using MSVC like support? It also knows about garbage collection on or off. It knows about signed overflow. So for example, here, just to like show what you could do, you could access the is signed overflow defined or not. So there's a command line flag that you could change this. And then you can also access the file name. And then at the end, there's also end source file action. And in between, there is execute action, which we didn't override here, but it does call create AST consumer. And here we're just creating a consumer. And then later on, Clang will just walk the AST and with your consumer and call the consumer at various points in the AST. So the next point would be a consumer. So that's like the next step in the pipeline. There's a little bit of boilerplate always associated. And this is actually exactly the boilerplate that Clang tidy got rid of. So if you're running a Clang tidy check, you're just going to be writing this, like the main point here. But here, again, the idea of like writing a Clang tool or a libtooling tool is that you have the main function, so you can do lots more things. You have lots more power. So the next step was the consumer. And the consumer here is using, all it really does, it creates a matcher. So what lib tooling or clang tooling in general is really, really good at is finding a very specific node in the AST. So if you're writing like a style checker, you want to find pointers, clang gives you lots of possibilities of finding that exact like node in the AST very efficiently and effectively. And for this, clang actually has a domain-specific language under the clang AST matchers library. And it has like these macros where you can define almost like in plain English what you're looking for. So for example, in our case, we're looking for all functions. We want to compute the complexity of functions. And so we were looking for functions that are in the main file. So this is like in system header, the opposite is in main file. And then we can bind some of these nodes to variables. And later on, we can access them. Then we create a match finder, which is part of the library. We add the handler, which is what we have up here, on top, to the matcher. And then inside handle translation unit, we would just tell Clang to run our handler on the AST. So instead of like handle translation unit, there's also a few more points where we can access the AST, like handle like inline function declaration, handle vtable declaration. And the point here is that at this point, the AST is already parsed, so we can access it at several steps. And then the main class is this match handler, which is also part of the AST matches library. And it will be called for every node that matches this expression below that we had for the functions. And inside here, we'll be actually computing the computational complexity. And for this, actually, for this particular tool, I have some more slides. I have one slide. No. Okay. All right, so what is cyclomatic complexity? Cyclomatic complexity generally computes the number of paths through a program. So if, for example, in this case here, we have a very basic if clause, and this is the control flow graph for this if clause. So we have some start node, and all of these nodes here are basic blocks. So if you don't know what a basic block is, a basic block is any part of your code with exactly one entry point and exactly one exit point. So it's basically any piece of code that has no control flow in it. And then if you have a control flow graph, the nodes are the basic blocks, and the edges between the basic blocks are the control flow. So for example, in this case, the first node would be int x equals f, and up to x greater 5, that's the first basic block. Then we have control flow. So we have an if statement, here the x plus equals 1, or an else branch, and then they both join together back at the return x. And so in this case here, we have two paths from start to end, like the left path or the right path. And now if we added more complexity, like here I just added one if clause, that's what I added, then we get another path. So now we have three paths here. And so the cyclomatic complexity, or the Maccabi index for this function would be 3. And if it's like, if you add more control flow, it maybe becomes like more than 5, more than 6. At that point, you maybe like want to try refactoring or like rethinking your control flow. And so one interesting way of like thinking about this number here is that if you think of the minimum spanning tree through this graph, so like if you think of some tree that passes through every node, but like with no cycles. So for example, in this case, you would have like this. Can we see my cursor? Yeah. So this path here, and this path here. So this like here is one minimum spanning tree. Then all the edges that are not in this minimum spanning tree are additional paths and additional complexity. So like this, if there was only this, the Maccabi index would be 1. And for every edge that's not in this minimum spanning tree, the Maccabi index is one greater, because you have one more path through your program. So you have like this path, or this path, or this path. And so the way we compute this is actually extremely trivial. So we have this match handler. We get a match result. And the result contains, most importantly, the nodes that we bound. So here, for example, we get the result has some nodes, and we can call getNodeAs and access some node that we previously marked. For example, like here we had .f or just fn. So we can get the fn node, and we can get it as a function declaration. And once we have this function, there's this nice method called buildCFG. And this builds a graph consisting of basic blocks. So it's basically just a bag of basic blocks in the order that they appear in the control flow. And so we get this control flow graph. And all we need to do now is compute the number of nodes and the number of edges. So yes?
I have a question. As far as I remember, you could just count the number of if statements and while, wherever you have a condition that branches, and just add one, and you're done with Mackay. Without constructing all the graph structure that you are doing here now.
that might, sorry, the question was, could you just count the number of ifs and number of while clauses? Yeah, like, I mean, intuitively it sounds simple. I'm sure, like, if that were the case, you would do it. But yeah, it's true that for every branch you get one extra level, one extra path, and for every while statement. I mean, for a while statement, there's a few more nodes because you have the condition, then you have the loop back. So it's maybe a bit less simple.
I think all your switch and other things also might contribute, right?
Yeah, I was
Yeah.
deviation.
Okay.
Yeah, so I'm sure there's ways around it. There is like a formula to compute those numbers. Basically just the number of edges minus the number of nodes plus 2 times the number of components in the graph. So component would be like, if you had many functions, there would be many components of the graph. In this case, it's just like 2 times 1 because there's one component. And then we need the number of edges, and we need the number of nodes. And that's all we're doing here. Like number of nodes, it's just the size of the control flow graph minus 2. It's minus 2 because Clang adds an entry and an exit node at the end and beginning of the CFG. So we just subtract those. And then we just iterate through the basic blocks and count the out degree, so the outgoing edges for each block. And that gives us the number of edges in the entire graph. And once we have that, we can compute this complexity. And then this tool also has like a threshold parameter. We check if the complexity is below this threshold and return if so. And otherwise, we emit a warning, a diagnostic. And diagnostics are actually very cool in Clang. I even wrote a blog post about it. So diagnostics allows us to use all the power of Clang diagnostics for our own tools. And as we all know, Clang diagnostics are really awesome. They're a lot more awesome than GCC diagnostics, especially for templates. And we have a lot of power here, and it's actually very fun to use it. Yes?
Just in terms of the control flow graph here, does this have a large number of control flows if you've got lots of exceptional routes through your code? This might be an answer for Peter's question.
So the question was if you have
exceptions as a possible control flow.
Yeah.
They don't show up as ifs and then anything else, and they create a large number of potential control flows if you've got functions taking and returning by value.
Yeah, I mean, I would imagine like if you had an exception, that would be like an outgoing edge, or would be like an exit node. Yeah. So that would most likely that would be an extra level of control flow as well. I would suppose.
That would give you a big number for some very simple looking code.
Yeah, I would agree. Yeah. I mean, you can try it out yourself then. So what we want to do here is a diagnostic, and for this let's just see how you do this. So diagnostics, you get a diagnostics engine from Clang. A diagnostics engine basically gives you access to all the diagnostics power. And then we get a custom ID for a diagnostic. And this is actually important because Clang has a lot of its own internal warnings that it can, has parameters that it can reuse in certain different scenarios. And in our case also, we need a custom ID. We also pass as a severity, so you can have a note, you can have a warning or error or fatal. In this case, it's just a warning. And then there's a formatting library here as well. So you can say a function with a name is too complex, and here we would pass the complexity. And then we get a diagnostics builder from this report function where we pass the location, where it's going to point the caret and the ID. And then we add a string, in this case the qualified name of the function, and we add a tagged val with a complexity. So this tagged val function is actually quite funny because it takes either a pointer or an integer. So again, as you saw, LLVM is quite loose on the boundary between pointers and integers as long as it's fast. So this function takes either a pointer or an integer, and you need to tell it if it's a pointer or an integer. But essentially, what we get at the end of this is if we go here. So we have some functions, right? So we have some function f here. It has one path, so Maccabi index should be 1. It has a function g that has 1 unit of control flow. And we have a function f that is way too complex that you'd want to change, right? So this could be your code. And then we can call Maccabi on this, CPP. And there's also a threshold parameter. So if we just set it to 0 for a second, then in this case, it would, for each function, compute the Maccabi index. If the index is higher than our threshold, it just emits a warning. And here you can see how nice Clang diagnostics are. They're even have colors. So we have our message here. The name of the function is too complex, and the index in the parentheses. And then also the caret pointing at the function. And then what we could do in this case is usually you would say the threshold should be 5. and then only those functions that are too complex would actually show up. And if this were your code, you would probably want to think about rewriting your code in this case. And this done with the heart here was just to show what you can do at the end of the action. So like you can have an end source file action. At this point, for example, if you're writing a source-to-source transformation tool like clang format, this would be where you like print out the changed file. Okay, how much time do we have left?
35 minutes.
Okay, so we can do at least one more, I think. So we had, what's the next one? Include sorter. Okay. So include sorter, I didn't actually think people were interested because clang format does that anyway. But it's actually cool because include sorting means we only deal with the preprocessor. So this shows you how you can access the preprocessor and look at like if-defs, or in this case include directives. So we have our boilerplate again, like clang tool. We have some options. And in this case, we have an action and only one preprocess, one consumer. So there's not 3 nodes in this case. There's just 1. So we have an action, and we have an option to sort our includes or sort them in reverse order. So we just pass that to the action. And then we have begin invocation. So this I didn't show before, but before begin source file, there's also begin invocation, which is called before any file is even touched. So in this case here, what we do is we get a rewriter. So Clang has this nice rewriter data structure, which is like a fancy B tree, which allows you to, like it implements a rope and allows you to rewrite your source code very efficiently. And so we have a rewriter. We tell it the source manager, which manages all the translation units in your code, and the language options. And then inside begin source file action, what we're going to do is create our callback. So this is the class above. And then get the preprocessor from the compiler and just add a pp callback. And that's really all there is to it. So we add this callback. And then what we can do with this callback is enter the preprocessing at various stages. So in this case here, I overrode inclusion directive. But you could also override like if, or override if-def. So if you wanted to do some fancier analysis on the preprocessor, you could do that with the pp callbacks. In this case, what we want to do is we want to sort includes. So one thing we have to think about here is that usually, like in this case, or many people like to sort their includes in like blocks. So our algorithm here is going to be look at every include directive, look at the line, and if the line number is more than 1 from like the distance is more than 1 from the previous line, we have like a block. So sort everything we saw up to there, and then rewrite the source code for that particular block. So here's this include data structure, which just has a file name and tells us whether or not it was like angled, so a library inclusion. And then the actual callback here, okay, so it gets the location of the include, it gets the inclusion token, which we don't need here, the file name, whether or not it's angled, the range of the entire inclusion directive, the file name, absolute path, real path, and the module. So Clang actually already has like support for modules. In this case, this was already there before, so it's just more of a general idea of like some unit of code. But yeah, so what we have here then is we get the location, which is the location of the hash, and we check if it's in the main file. If not, we just return. Otherwise, we also sort all the standard includes, which is there's too many. Then we use C++17 to get the file ID and the offset of the location. The reason we need this is that we later on need to get the line number, so we can check if the distance is more than 1. So we get a file ID, which is just like the identification for the file, and the offset from the source manager. So that's what the source manager is good for. And then we call get line number. So this is a bit nicer than you saw before in libclang. We just pass it the file, the offset. This here is of course not very idiomatic, but like we also pass it a output parameter to check if there was an error. But anyway, we get a line number, and then here the idea was that either if we already have some includes, and if this line number is greater than the last line number plus 1, then we have a block in our include so far. So there's down here we have like this vector of includes. At this point, I just want to like shout out for the data structures inside LLVM. They're really awesome because they actually give you, like as a developer, lots of options and make like conscious decisions about the data structures you use. I think I even have, so like quick digression, I even have this open here. So these are all the data structures you can use inside LLVM. There's a lot more than the nasty ones in the standard, especially for hash tables. But one very common optimization you see in LLVM is using small things. So here you just saw a small vector, And the idea is like the small string optimization for strings. You just allocate a fixed size buffer, and if you need more, then you allocate more space. But for example, you have like small vector, you have tiny pointer vector, which I believe like it either stores, it has a pointer, and it can either store like if it's a 64-bit system, you can either store 8 bytes, like a container for 8 bytes, or it reuses that same pointer to point to an actual data structure. Then you have like some like lots of small sets, string sets, dense sets, index map, B trees, twine. Twine is actually very nice. It allows you to. It builds like a tree of temporary string expressions, so that you can like concatenate lots of different strings together and turn them into an actual string at the end. I think I have an example later. But so let's just go back here. So what we want to do is, if we so let's just say this is the first include. We get the location of the include, and what we want to do is we want to record the first location and the last location of a block, so that later on when we sort them, we know where to replace the sorted includes. Then we in-place back the file name and whether or not the include was angled. We get the last line number and the last location, just so that we can do this more efficiently here. And then, so for the next include, if the new include had a line number that was more than 1 away from the last one, for example, if we just got to this one here, that means that currently in our include vector we have all of these includes, and we want to sort these includes. So to sort the includes, we call sort currents, which calls sort includes. And this function here just basically takes the vector of includes. So here is a small vector impl. So if you saw Chandler's talk on data structures, you know that LLVM likes to use polymorphism to do lots of its small optimization. So for example, the small vector actually derives from small vector impl, which means that you can have this small buffer inside the small vector, but when you have a function, you can just take a small vector impl, and the whole buffer is actually abstracted away. So this is actually very nice. So we sort our includes, either in reverse order or not reverse order. Again, these includes are this data structure up here. We sort them, and then we just join them all together. And this is basically just joining them and possibly adding angles. And this here uses this awesome twine data structure. I'm a big fan of this. So what it does actually, it's like a recursive data structure. So when you create a twine here, it'll create a temporary twine. And then when you add it, add like this const care pointer here, it'll create another twine. And so progressively actually build up a tree of twines that are all temporary expressions. So if I were to store this line here, like if I were to like store this in a variable, it would be complete garbage because all of these temporary expressions would be deallocated by that point. But what we can do is like as a temporary expression, build up a tree of twines, and at the end just call dot string and have like one big concatenation. So you would know exactly what the length of this temporary expression is, build one string, and just throw everything into the string. And that's really cool. So we just sort the includes, return the joined lines, and then if we go back to here, we have the range from the first location to the last location, and then we just replace the text. So we just get this range, replace it with this text, and that's all there is to it. And like clear the includes for the next time. And then the only thing that's here is that because of the way this is structured, for the last block, there won't be an include that's more than one away. So like also at the end of the main file where we can also like jump in, we also want to sort one more time. So let's try it out. Are there any questions? Oh. Okay. I imagine everyone is asleep by now.
Not yet.
Okay. Okay, so what's here? So this is actually just the includes from before. You can imagine what it should do, hopefully, is take these lines and sort them. So include sorter. So this is exactly what you mentioned before, like what I need to pass some command line parameters. And here, I need to also tell it that it's C++14. And then it works. Okay, so here it actually included, it sorted the includes. One second. And then just to reassure us that it actually works, we can sort them in reverse order. And that works very nicely. And it also sorts them within the blocks, which is cool. Some people also told me that it would be nice to additionally like sort the blocks. This is also something what you usually want to do. Like sort the standard includes at the very bottom, then like more and more specific, like clang includes, LVM includes, project includes. That could be like the next step. But yeah.
Since you were only going through the preprocessor here, why would you need to include the record? Are you still building the entire translation unit, and could you have actually not had to do that? If you're just like, I just want to preprocess something.
Yeah, that's a good question. I believe it does not like create the entire AST. Nevertheless, one thing Clang is very picky about is actually having like a valid AST. So I imagine it still actually checks if those includes exist, probably as part of the, like it probably has its own inclusion directive base method, which checks if the include exists as part of their pre-processing. So one problem with this Clang is that it actually needs to compile your code. Like it actually needs to know all the includes, and to know all the flags to compile. So it might actually also like take a while sometimes if you use a Clang tool. Like if you ever use like include what you use, it sometimes takes half an hour to work on a big project. Yeah.
Yeah. One of the reasons for that is, if you're manipulating the AST, well, it needs to know like what all the flags are, because that affects the AST.
Yeah, sure. Like if
you have a -d blah 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 blah, and so then the if-defs come into play. And,
or the the standard as well, for example. Yeah, definitely. I mean, but actually, the thing is that Clang format does some magic to work around this. So Clang format works without it actually having to compile, which is actually like if you use Clang format, you also don't have to pass it these includes. So I'm not sure what it does, but it does something nice so that even if your program doesn't compile, it still works. Whereas here, if you have a bug somewhere in your code, it won't work. But yeah, so you have to pass it everything. Okay, yes?
So I guess you can bypass the check by adding actions. So if the code is in the driver, the Clang driver,
Yeah.
you can say that, okay, just don't do this action when a particular flag is bad. And that way you can completely bypass any kind of check, especially for like trigger things like include sorting. You don't really need to, if you don't want to have the entire AST,
Yeah.
you can do it.
Yeah, I'm sure there's ways around it.
It's very complicated.
Yeah, I mean, one thing that's actually important to know about Clang tooling is that very often what you think you would be able to do with Clang tooling is actually modify the AST. But when you use Clang tooling, you will never actually modify the AST. You can't just like make something const or like add a node, because Clang has very strong invariance about its AST. It has to be valid. This is actually also one of the reasons why we don't have custom attributes yet, because if Clang doesn't know the attribute, then it just like thinks the AST is invalid and it'll just throw it away. So this means that whenever you use Clang tooling, all you're going to ever do is change the source code. So for example, in this case, we used a rewriter to rewrite the source code, and that's what you can do. And you can change the source code, but you can't change the AST, because that might break something. There might be lots of invariants in places where you don't expect them. So you can't actually ever change the AST.
Although you could change the source and then regenerate another AST.
Yeah, I mean, there's also like nothing to stop you from actually like making a node const or something. Like the methods are there, but it just might break stuff. Yeah, like I mean, the methods are there. Like you can use the source manager to make a node const or something, or you can add a new child. So I think that's possible. You might have to like reparse, and I've never done it, but it's definitely not encouraged. Yes.
So you said that custom attributes are not supported, which is weird, because if I wanted to write a tool that, let's say, collects all of the widgetable members of a class.
Yeah. Yeah, so the question is, can you use custom attributes at all or not? Yeah, so this is actually true. It's not possible right now. I think it's something people are working on. I actually tried myself to do something once with attributes. Like I wanted to do like a memorize. Like in Python, you have this memorize decorator, which tells Python to put a cache in front of every function. And I wanted to do that in Clang as well, but it's not possible with an attribute. So the one thing that is possible is that you can actually, like if you have some class here, what you can do is that you can use these GCC attributes, like attribute. I think no, it's something different, but like if you can use something like that, and you can add a custom like tag. So this annotate is like a GCC extension that Clang supports, where you can pass any kind of string. And then later on, what you can do, and this is how I solve this memorization problem, is that you can actually look for all nodes that have this annotation, and where this annotation string is this value. It's not nice, it's especially this like attribute thing, and it's definitely not as nice as an attribute, but it is possible, but just not with the C++ 17 attributes yet. But hopefully in the future. Like, I mean, that's definitely, I think, one thing that C++ is lacking compared to like Java, which has like these decorators, Python annotations. I think that's something that C++ could really use. Okay, are there any questions about include sorting? Otherwise, we have like 15 minutes left. Might be time to just like quickly walk through one more. The next one was pointer finder. Yeah, so pointer finder, let me just think. One thing, I'm just actually going to swap, because we don't have much time. I just want to show you how fancy the matching can be. I'm going to do the clang variables. So again, clang variables was the const auto lambdas that have an auto parameter that are no except and have a goto inside. And I also want to show you how you can do this matching yourself. Let me just go up here. Up. So say you have some code like this here, right? So you have some code, and you want to figure out, like you want to make sure that this code has a certain prefix. What do you do? So the first thing you would do is you do this ast dump that I showed you before. So a clang ast dump f syntax only test.cpp. And right, so this is also why like excluding system headers is often a good idea. But so what we have here is the AST for this particular function, right? So we can see, for example, and this is actually quite interesting, what a lambda is, of course, is nothing else than a class, like a class that the compiler creates itself. So we have at this point here somewhere a CXX, I think it's actually this one here. There's probably
Lambda at test.cpp 1.22.
Yeah, I think. Oh, here. Might be. But yeah, so this is the CXX record decal that's actually declared, right? So you can see this AST. And now what we're interested in is finding out, like, how do I access this one node that I want? So here I can see a lambda is a CXX record decal. It has, because this has an auto parameter, it has the actual call operator will be a template. And then so you have a CXX method decal. This has a compound statement, which inside somewhere has an if statement and then a goto statement. And I think somewhere also there's like a no except declared. So the first thing you would want to do is like look at the AST and figure out what nodes you want to look for. And then you can imagine that like Clang tooling people are kind of into tools. So they made a tool to help them write tools. This tool is called Clang Query, and it's actually very useful. So what Clang Query allows us to do is basically like interactively match on the AST. So for example, in this case here, we're looking for, I think, like all var declarations.
People out here can't see the last line, the one you're typing on.
Oh, okay. So let me, yeah, that's the problem because here I can't actually like scroll up. Is that better? Okay, let's just do this. Yeah. Okay, so you could look like for all variable declarations, and it'll look like tell you what they are, and then you can ask like what more is there, right? So I want all things that are in the main file and not in the system header, and I want all variable declarations that are that has a initializer, init list expression, for example, right? So with this tool here, you can actually figure out this very complex AST matching expression that you need in this case, which is here, using this tool. And this is actually very important, and without it, it would be very hard. So the boilerplate is the same. The only thing that's interesting here is like the actual matching. So what we're looking for here is a variable declaration. And the nice thing is that it really like reads like proper English. So you have we're looking for a variable declaration that is expanded in the main file that has a type which is const qualified, like the C in the Clang, that has an initializer which has a type CXX record decal, which is the lambda. That is a lambda that has a function template decal because it takes an auto parameter. That has a method inside, which is the call operator, which is no except, and which is a body, which is a compound statement, which has a goto statement. And then all of this I can bind to the Clang name, right? And then up here in my matcher, all I need to do is I get the Clang variable, and this would be the same for the pointer finder, by the way. So I just get the node, and and I get the name, and I check if the name is empty because you'd have a variable without a name. And if it's not empty, I want to make sure that it has this prefix. So the pointer finder would be p underscore. In this case, I want it to be clang underscore. And then all I need to do is warn the user about it. And here also you'll actually also see fixits. And so Clang has this cool thing called fixits, which actually tells you if you're doing something wrong, and actually tells you how to fix it. So if the name doesn't start with Clang, then we want to emit a diagnostic. So we get the diagnostics engine, we get an ID for our diagnostic, and then we create a fixit. So what a fixit will do is display to the user some way of fixing a problem, right? So in this case here, I want to make an insertion because I want to tell the user you should actually have a clang underscore before the variable name. So I create an insertion at the point of the variable. The prefix should be clang underscore, and then I add this fixit hint to the builder. And then if I actually use it, clang variables, test.cpp. Oh, I'm not in the Docker anymore. Clang variables, test.cpp. And nope. Okay, right. And so I emit a diagnostic for the variable name. I tell the user to have a prefix clang underscore before this. And then also, like, if you add a little bit more effort, you can also add an option to rewrite the source code inline. So Clang itself actually has this. So if you have some code, let me actually just like quickly write something. So if so if you have like some X and you forget a semicolon, right? So this is actually where Clang really shines compared to GCC. Like if I compile this, I don't know if I have GCC on this Docker. I do. So x.cpp. No, I might not have G++. Anyway, so if I do this with Clang, then the cool thing about Clang is that it actually tells you the actual problem. So what GCC would do here in this case, it would say that at the next line, the first character of the next declaration, it would say there's something wrong, like did not expect a declaration here, but Clang actually figures out that you missed a semicolon. And it also shows you how to fix it with this like green underscore. And then I believe if I pass xclang fixit, that will do something, I hope. x.cpp, and actually fix it, right? So this is really cool. So the Clang already supports this. And if you add a little bit of effort, you can also support this in your own Clang tools. So this is pretty cool. All right, so we have 10 minutes left. I think I'd like to use this just for any questions you have on Clang tooling or LLVM in general. Yes?
So you mentioned a bit about how the libtooling API isn't as stable
Yeah.
as the libclang API. How rapidly does it change, and how much do you have to usually do to port your code to the new system?
Yeah, so the question was like, how rapidly does the libtooling API change? It changes to the extent that any tutorial you find online is not going to compile. Like everything from a year ago, like Eli Bendersky has lots of cool tutorials on Clang, but nothing compiles. Like it's all broken because something has changed in the AST. Some method doesn't work anymore, or something like this AST matching was only added like in the last 2 years or something. So anything before that is not going to work, or uses like old methods. So very rapidly. Yeah.
Are there any best practices for handling multiple versions of Clang?
I'm not sure if there's best practices. Like I would just say, I mean, if you have time, just like always try to keep it up to date with the trunk version. Like in this case here, this is like Clang 4.0, which is already available. And like if I think it's like with your normal source code, like if you just stick to some compiler for like half a year, and then because it supports the standard you want, then just it's going to be fine for that compiler because nothing is going to change in the meantime.
For OS compatibility reasons, we need to support 3.7, 3.8, and 3.9.
Yeah, like if you're lucky, those versions are going to be more or less the same. Otherwise, I'm sure you could figure out like maybe you have to do some if-defs. Otherwise, I'm sure there's a standard way around it, because I imagine mostly things were added since then. So I would hope that it still works. But yeah, it shouldn't be too hard, I think. Yeah. Yes. Any more questions? No. More questions? Otherwise, I do have a few outro slides. One is about ClangD. So ClangD is a very new project, like I just heard of straight from LLVM conference a few months ago or a few weeks ago. ClangD is going to be a language server. So this is actually very cool. It's going to be an editor agnostic background daemon that runs on your system, and that different editors like Eclipse or Atom or Xcode or Visual Studio, whatever you use, can actually communicate with. And this is actually very important because what ClangD will allow you to do is like make, I don't know, RPC calls or something like that, or communicate over a socket, and get code completion, get indexing, get linting, get formatting, like basically get Clang as a service on your system, and that's going to be pretty big. At the same time, it's like, I mean, I was going to say it's nowhere near stable. They actually already have quite a few things. Like they have code completion, they have linting. Right now, they're figuring out the indexing strategy. One second, but yeah, so it's still a work in progress. And if you're interested, in just talk to me, and I'll point you in directions. Yes.
Is it what kind of API is it using? Is it using the API that Microsoft?
Yeah, the Microsoft server language server protocols. It's an implementation of that. Yeah. Yeah. Okay. So it's very early development. Like there's just 1 or 2 guys working on it, but it's very promising. So if you want to help out, please do. And then also, like, how do I continue? So this talk was not necessarily about me being an expert, but me just like sharing the learning experience. I also want to like point you in some directions. One point is Eli Berndersky's blog. So this is a Googler working on the TensorFlow team. Actually, he works on this compiler using LLVM that compiles the computational graphs for TensorFlow. But he also has loads of posts on Clang and LLVM, which are very interesting. Then, like I would say, LLVM and Clang internals. So there's actually, even though the inline source documentation is not too extensive, there's lots of resources externally. Like so, before you saw this programmer's manual, like there's just like a whole document on everything about learning how to use LLVM. There's the same thing for Clang. There's the same thing for like AST matching. So just like use those resources. Then there's this blog by a person that may be me. That has some blog posts on Clang. I'm also going to put all these other tools that I have here up online, so you can use them and just like pull the Docker. It should take like 3 minutes, and then you can try out all these different tools. They're all documented, so you can see what they do, and maybe take it from there for your own tools. And then the source code. So as you saw, I'm very excited about the Clang source code. It's very, very nice code. It uses very, like, the people working on it are extremely smart and extremely performance paranoid. So, like, it's very educational to look at the code and see how they do it, and maybe also fix all the things they did wrong. But yeah, so and the slides are going to be up there later on, including the code and the server. If you want to like look at my server, you can also look at the server. Okay, thanks. So this is going to be Q&A, but I think we can skip that. So yeah, thanks.